When you adjust the heat under a kettle, you don't think in absolute extremes. You turn the dial to a little hotter or mostly simmering. Humans navigate the physical world using degrees of intensity. But historically, machines have been programmed to evaluate this same environment using strict binary states. Traditional control systems rely entirely on classical logic. To govern a physical process, engineers must define a precise mathematical model of the system and establish an exact calculated objective function that the machine must hit. The strict limitation of these classical models is that they require the physical environment to be categorized in rigid terms. A condition is evaluated as either entirely true or entirely false. It is a 1 or a 0. This Boolean logic breaks down when applied to continuous real-world systems. In physical reality, absolute boundaries rarely exist. A room does not instantly snap from cold to hot the moment the temperature rises by a single tenth of a degree. This diagram illustrates the problem. If we ask a classical system, "Is the water hot?" the top half shows the only allowed answers: an absolute yes, represented mathematically as a 1, or an absolute no, represented as a 0. To handle varying degrees of truth, engineers use a mathematical framework called fuzzy logic. Looking at the bottom section, the same question now yields a continuous gradient of responses, translating states like very much or little into functional data. Notice the decimals: 0.9, 0.25, and 0.1. Fuzzy logic allows elements to have partial membership within a dataset. A temperature can be 90% hot and 10% warm at the exact same time. By assigning this partial membership to data, engineers can mathematically encode heuristic, human-like expertise. It provides a way to map our intuitive understanding of the world directly into deterministic models that govern complex physical systems. Moving past the conceptual framework, we need to look at how fuzzy logic is actually calculated. In classical set theory, an element is either in the set or out. A fuzzy set, functioning within a defined universe of information, is represented mathematically as a specific set of ordered pairs. The core mathematical differentiator in these ordered pairs is the membership function, denoted by the Greek letter mu as a function of the variable y. The membership function is the mathematical formula that assigns the precise degree of truth to any given input. This graph plots a universe of information variable y on the x-axis against its calculated membership degree, mu, on the y-axis. The membership function is strictly locked between the numerical boundaries of 0 and 1 on the y-axis. Any value that falls along the curve between these two boundaries, for instance 0.6, represents a mathematically valid partial truth. When the universe of information is discrete and finite, the fuzzy set uses a summation symbol over individual data points. Conversely, for a continuous and infinite universe, those points become a smooth line, and notation shifts to an integral symbol. In fuzzy set theory, these summation and integral symbols do not denote arithmetic addition. They simply represent the collection of all elements within the set. By locking degrees of truth onto this continuous scale, imprecision is formally quantified. It is a computable variable. Having defined single fuzzy sets, the next step is making them interact with one another to form operational logic. This visual traces the union relation, also known as the fuzzy OR operator. In fuzzy mathematics, the union operator evaluates the overlap and executes a max operation, selecting the highest points of membership from either set. This diagram shows the intersection relation, which functions as the fuzzy AND operator. Here, the intersection operator evaluates the two sets and executes a min mathematical operation, tracing the lowest inner boundary where the shapes overlap. Finally, there is the complement relation, or the fuzzy NOT operator, which inverts the original set and mirrors downwards from the top of the scale. The complement is derived by taking the exact degree of membership for any given point and subtracting it from 1. Even though we are using min and max functions instead of binary logic, standard classical set properties still hold true. Commutative, distributive, and idempotency laws govern these sets just as they do crisp ones. De Morgan's law also remains entirely intact, preserving the system's ability to logically prove tautologies and contradictions. These specific mathematical operators are the engine of fuzzy logic. They allow engineers to take complex, language-based rules and execute them entirely through arithmetic. The ultimate application of this mathematics is the Fuzzy Logic Control Architecture, or FLC. Before an FLC can be engineered, strict prerequisites must be met. The physical plant being controlled must be observable, and a concrete body of linguistic rules must exist to map the input-output relationships. This schematic outlines the complete architecture that bridges physical reality with heuristic logic. The process begins on the left with the ordinary set. This represents a crisp, precise physical measurement taken directly from the environment, like the speed of a rotor. Step 1 is fuzzification. This process converts those rigid, crisp values into fuzzy degrees of membership. Step 2 utilizes the fuzzy knowledge base. This stores the membership functions and maps the known relationships between inputs and desired outputs. Working within that base is the fuzzy rule base, which applies human-designed linguistic if-then rules directly to the process domain. Step 3 is the inference engine. Acting as the kernel of the system, it simulates human approximate reasoning by evaluating all activated rules simultaneously to reach a decision. Because multiple rules can trigger at once, the system moves to the aggregation phase. The outcomes of the multiple rules are mathematically combined into a single complex shape known as the output fuzzy region. The physical world cannot act on a fuzzy region. Step 4 is defuzzification, the critical final process that forces the aggregated fuzzy logic back into a precise number. Engineers often use the centroid method here. This calculates the center of gravity of the output fuzzy region to extract the single expected value. This process yields an actionable, crisp, ordinary set output, ready to be sent to a valve or motor to physically alter the plant. The FLC acts as a rigid mathematical translation layer, sandwiching imprecise human heuristic logic safely between precise physical inputs and precise physical outputs. Deploying this control paradigm in the field comes with specific engineering trade-offs. The primary advantage is extreme robustness compared to traditional PID controllers. A PID controller, which calculates error using proportional, integral, and derivative terms, requires a highly precise mathematical model of the system to function. A fuzzy logic controller does not. This robustness allows the system to seamlessly cover massive, unpredictable ranges of operating conditions. In environments with sudden fluctuations, a fuzzy controller adjusts dynamically, where classical control systems would fail. The trade-off for this capability is a heavy reliance on historical data. To properly tune the rules and membership functions, the FLC requires massive datasets representing past operations. There is also an operational bottleneck. System accuracy is entirely dependent on the high level of human expertise programmed into the rule base. If the linguistic logic is flawed, the controller fails. Furthermore, the linguistic rules must be regularly updated over time to account for mechanical wear or shifts in the operating environment. Otherwise, system efficiency decays. Fuzzy logic does not eliminate precision. It mathematically masters imprecision, turning human intuition into a deterministic engineering tool.